Hello everybody, myself Jyoti and this is fifth lecture on Raman spectra. Here today we are going to study about the how the molecules are classified according to their rotational behavior. So earlier when we studied the spectra of diatomic molecules, our focus on was on diatomic molecules. Diatomic molecules, they are linear molecules. So till now we are studying linear molecules. Now, when we consider a diatomic molecule, the molecule rotates about an axis passing through its center of mass and perpendicular to the internuclear axis. Now, same is true for other linear molecules as well. But what about the polyatomic molecules? So, when we try to study the rotations in polyatomic molecules, the behavior is complicated. But if we assume that, or if these molecules they possess certain symmetries, their study becomes very much simple. So what we have to study today is what are the symmetries possessed by different types of molecules. In classical mechanics, we have studied about the three mutually perpendicular principal axes and corresponding principal moments of inertia of a body. So we have three principal axes, x, y, and z, which are mutually perpendicular to each other. And along these three principal axes, we consider three principal moments of inertia, ix, iy, and iz. So if a molecule has an axial symmetry, then the axis of symmetry, surely it will be one of the principal axis. Now, depending upon how this moment of inertia is about three principal axes, we can classify the molecules. In a sphere, any three mutually perpendicular axes can be chosen as a principal axis. The rotational energy levels and hence the rotational spectrum of a molecule depends on its symmetries. And now we will study how these molecules are classified. So we have basically four types of molecules. First is linear molecule, then symmetric top molecule, spherical top molecule, and asymmetric top molecule. So let us study what are these molecules one by one. So linear molecule. So in case of linear molecules, the internuclear axis is the only axis of symmetry. What is internuclear axis? The axis which joins the two atoms together in a molecule, or you can call it as a bond axis. Now let the axis of symmetry be x-axis. Suppose we are taking that axis of symmetry along x-axis. The moment of inertia about this axis, it is negligible and we can take that as 0. So in case of linear molecules, what we have is Ix equals to 0. That means principal moment of inertia along the axis of symmetry, it is 0. And suppose moment of inertia about y-axis and z-axis, it is constant. Suppose that is equals to I. Now, in such molecules, the separation of lines in rotational spectrum are related directly with the moment of inertia I that we have studied already in the spectra of diatomic molecules, because diatomic molecule, it is a linear molecule. And knowing the atomic masses in the molecule, bond lengths can be calculated using the formula I is equals to mu r square. So mu is reduced mass of the molecule. If you know mu, then you can find out I just by knowing the value of bond axis. So example of linear molecules are O2, carbon monoxide, carbon dioxide, C2H2, that is acetylene. These are the few examples of linear molecules. Now, what is the difference between linear molecule and symmetric top molecule? Now, symmetric top molecules, they also have one axis of symmetry, suppose x-axis. And here, Ix is not negligibly small. In case of linear molecules, we have Ix, that is principal moment of inertia along x-axis, equals to 0. This is not the case in case of symmetric top molecules. In symmetric top molecules, Ix is not equals to 0 and Iy equals to Iz equals to I. So if Ix is not equals to I, there are two cases. Either I is greater than Ix or I is less than Iy. So if moment of inertia along y and z axis, it is greater than principal moment of inertia along x axis, that kind of symmetric top molecule, it is called as a prolate symmetric top molecule. And if moment of inertia along y and z axis, it is less than ix, यहाँ पे ix चाहिए, हाँ, there is a mistake. If I less than ix, that is the principal moment of inertia along y axis and z axis, it is suppose less than ix, this is ix. The symmetric top molecule is called as a oblate symmetric top molecule. Now, symmetric top molecules have polarizability ellipsoid, which is similar to one in the case of linear molecules. That is, they have linear cross section at right angles to the axis of symmetry. So that is, cross section becomes circular. Now, in spite of that, the Raman spectra is quite different from those of linear molecules, but nevertheless, they are instantly recognizable. If you consider symmetric top molecule and if you consider linear molecule, the spectra, it is very different. And from the spectra, the structure of symmetric tops, bond lengths, bond angles, all this we can calculate or we can deduce. Example of symmetric top molecules, suppose if I take oblate symmetric top molecules, benzene, ammonia, they are oblate type, and chloromethane, propine, they are prolate symmetric top molecules. Now, third case is spherical top molecules. So, spherical top molecules, it can be considered as a special case of symmetric tops with equal principal moments of inertia along the three perpendicular axes. So, that means in spherical top molecules, principal moment of inertia Ix, Iy and Iz, all these three are equal. And these molecules have the same polarizability in all the directions, that is, polarizability ellipsoid is spherical. And we know that in other cases the polarizability, it changes with the direction. Now, rotation of polarizability ellipsoid produces no change in the polarizability. Therefore, pure rotation of spherical top molecules are completely Raman inactive. Because when we have studied Raman spectra, Raman effect, that time we know that Raman spectra can be observed only for the molecules which can produce, in which the internal motions can produce change in polarizability. Here, in case of spherical top molecules, rotation of polarizability ellipsoid, it doesn't produce any change of polarizability, and that is how we cannot observe Raman spectra for these molecules, and they are completely inactive, Raman inactive. An example of Raman inactive spherical top molecules are carbon tetrachloride, sulfur hexafluoride, methane, and so on. Now, that is all about the different kinds of molecules. One is left, asymmetric top molecules. So in an asymmetric top molecules, all three principal moments are different. In spherical top molecules, we have all three principal moments of inertia equal. In case of asymmetry top molecules, all principal moments of inertia are different. That is, Ix not equals to Iy not equals to Iz, and so most of the large molecules, they are asymmetric tops, and normally all rotations of asymmetric top molecules are Raman active. That means the rotations in this kind of molecules, they produce change in the polarizability of the molecule, and that is how they are Raman active. Their Raman spectra are generally very complicated, and a simple interpretation of the spectra, it is usually not possible. Example of asymmetry top molecules, water, NO2, anthracene. So these are the asymmetry top molecules which are Raman active. Their spectra is complicated and we cannot give a simple interpretation of their spectra. So this is all about the four different types of molecules based on their rotational behavior. Thank you. Thank you so much.